Welcome once again to Physics 142 Online. What I'd like to do is walk you through the steps that you need to take in order to find an approximate value for the capacitance of a capacitor, and then show you how you're going to use this to do one of the homework problems. Remember, a capacitor is a device that can store charge. When we apply a potential difference or a voltage to the plates of the capacitor, then charge will flow, and we'll end up with positive charge on one side, negative charge on the other side. There will be a storage of that charge. We will later show how we can calculate the energy that's stored as well. But for now, we would like to understand how to find at least an approximate value for the capacitance. And remember that the capacitance is the ratio of the charge stored to the voltage that's used in order to charge it up. And so that'll be reviewed as we go through here. There's a four-step process for finding the capacitance of a capacitor, and here's how it goes. We first take the geometry, because that has to be specified for us to do the calculation. We have two plates, and we place a plus Q charge on one plate and a minus Q charge on the other plate. Of course, we don't do this physically, we're doing it conceptually. So we can analyze the situation after the capacitor has been charged up. So once we place these charges on the plates, then we want to find the electric field between the plates. And for this, we use Gauss's law, which is why we've spent so much time learning how to use Gauss's law to find the electric field in relatively high symmetry charge distributions. Then, once we've found the electric field, we'll use that and the definition of potential difference to calculate the potential difference between the two plates. A and B represent points on the two plates. So, having done steps 1 through 3, we now will have the potential difference between the plates. Since E, the electric field, will be calculated in terms of the charges, plus and minus Q, then we'll be able to do the final calculation for C as the ratio between Q and delta V. So, here's our picture for the parallel plate capacitor. And again, when we close the switch, and that parallel plate capacitor is connected to a power supply, electrons will flow from one side of the capacitor, the one labeled plus, all the way around through the battery, and they will be deposited, an excess amount of electrons will be deposited on the right-hand side. And it's that deposit of charge, plus Q and minus Q, that creates the electric field in between. So this is the example I'd like to do, the parallel plate capacitor. So we'll go through the steps. Place the charges plus and minus Q on the plates, and now we want to use Gauss's law to find the electric field in between. And once we understand the symmetry, that this electric field, as long as we stay away from the edges of the capacitor, will be a uniform electric field moving from the positive to the negative terminal, the negative plates of the capacitor, shown here by the red arrows. Once we see that that's the geometry of the electric field, then we'll want to draw a Gaussian cylinder. We could use a cube or a rectangular solid for this, but a cylinder is quite nice. We want to put one end of the cylinder inside the plate on the left-hand side, and then the other end of the cylinder we want to put in the region in between. The advantage to this is shown by the normal vectors that are shown for several of the surfaces for this cylinder. The surface on the right-hand side will have a normal vector going to the right along the direction of E. The unit vector on the curved part of the cylinder will be perpendicular to E, and of course the left-hand side of the cylinder, the unit vector would point to the left, but it's inside a conductor, and we know the electric field inside a conductor is 0. So here's how we do it. With the cylindrical Gaussian surface, then, we integrate the flux integral of E dot n hat dA through all three surfaces of the conductor. We know that there is a surface charge density sigma on these plates. And so I'm not going to work through all the steps, but this answer is one that we got something very similar to this before when we were using Gauss's law to find the electric field from a charged surface, and you end up with an electric field that's sigma divided by epsilon 0. So with that answer for the electric field, note that it does bear out our assumption that the electric field is uniform. Sigma is simply Q divided by A. That's a constant. Epsilon 0 is one of the fundamental constants of physics, so the electric field is uniform. And we then can substitute in, right, that sigma is Q over A, and we find the electric field is Q over sigma over epsilon 0 times A. Now we move on to step 3. Find the potential difference delta V between the two plates. And that's quite easy if we pick the right path. R and S are the two sides, the two plates that we want to use. And if we integrate from R to S, E dot dl will be integrating along the direction of the electric field, which will make this dot product really simple because E and dl will be parallel. Now, of course, as we've stressed before in class, delta V is independent of the path that we pick. We could pick some crazy path going from R to S, and as long as it began on R and ended on S, we would get the same answer. But because of that, let's pick the easy path. So the easy path is a straight line going from R to S. As we do that, E and dl are parallel, so delta V becomes the integral of E times dl. And then E, we've already shown that E is uniform. It doesn't depend on the horizontal position in between the plates, so it comes outside. We can substitute in for E as Q over epsilon naught A, bring it outside the integral, and then all that's left is the integral of dl from one plate to the other, and that simply is the sum of all the little distances going from R to S. As we add those all up, we get a value d, which is the plate separation. So delta V is Q over A epsilon naught times d. And the very last step, you can see what the result's going to be. It's very easy. We want to simply go to the definition of capacitance as Q over delta V. Well, Q, the numerator, is Q, right? And the denominator delta V is just Q over A epsilon naught times d. When we plug that into the denominator, we get the final answer for the capacitance of A epsilon 0 over d. Note, as we'll see on the next slide, that C does not depend on the charge, nor does it depend on the voltage. In fact, since it's the ratio of those two, then we have the situation, the capacitance is just a constant for this particular device. All it depends on is the plate area and the separation distance, in addition to the fundamental constant, epsilon 0. Okay, so that's important. So here's the result once again. As I said, C only depends on the physical parameters of the capacitor. If we change the plate area and if we change the separation distance, we'll have different values for C. But it only depends on the geometry and the size of this device. The physical parameters, of course, A and D, and it does not depend on the charge. I mentioned this in class. I said, what happens if we increase the charge placed on the plates? Well, the only thing that happens is the potential difference must increase as well, in just the way that would keep the ratio Q over delta V a constant. So capacitance does not depend on the charge. Capacitance does not depend on the potential difference. It tells us for a given delta V how much charge could be placed on the plates. And as we'll see in class, C also tells us how much energy can be stored in the capacitor for a given voltage. And that's useful to know if we want to use the capacitor as an energy storage device. So let's now set up and just talk through the setup of the homework problem, where you are asked to find an expression for the capacitance of a spherical capacitor. Okay, and you'll see this in your homework paper. The setup is this. You have two spherical shells, one of radius A, of course empty on the inside, another one of radius B. The region in between A and B is empty, and the region outside is empty. So the radius A and B should, we would expect, be in the final answer somehow, because the final answer only depends on the geometry. So A and B are the radii. That's part of the geometry. We place a plus and minus Q on the plates, and by placing a plus Q on the inside, that guarantees that the electric field will be radially outward in the region in between the conducting shells. That's just handy to have. It doesn't really affect the result, but putting it that way means that the electric field vectors will be radially outward. To find the electric field, of course, we're going to use a spherical Gaussian surface, You've done that before. The answer turns out to be fairly simple. Then with that expression for E, we're going to find the potential difference between the plates. And so we'll integrate from the inner surface at radius A out to the outer surface at radius B. And once again, the path does not influence the result. So let's pick a simple path. Let's integrate along the field line in the radial direction. So that means that dl in this expression for delta V will become dr times r hat, because it's the radial direction that that vector points in. Then, once you evaluate the integral, you'll know what delta V is. That will be in terms of Q. And finally, then, when we make the quotient Q divided by delta V, the Q will cancel out, and here's the result that you should expect to get. So, that is the outline for how to do it, and the meat of the problem is actually steps 2 and 3. Step 2 you've done before. When we did Gauss's law calculations, you did a problem just like this. Step 3 just involves being careful to do the integration correctly. And then step 4 is simple. So, hopefully this should get you started on that problem and show you what Gauss's law is really useful for in being able to help us estimate an expression for the capacitance of this arrangement of conductors. I'll see you in class.